Though the dominant interaction paradigm in modern gestural interfaces is still largely based on pointing and manipulation gestures, a different interaction paradigm has been gaining traction in the literature, that of motion correlation. In motion correlation interfaces, if every available target moves in a distinct way, matching its motion with the input device indicates to the system an intention to select that object. This principle has been successfully applied in a wide variety of contexts. For example, in orbits, we enabled eyes-only interaction with smartwatches using a wearable eye tracker. In PathSync, we demonstrated how the principle can be used with hand motions tracked by a Kinect sensor for interaction in public displays. In TraceMatch, we demonstrated how these gestures can be recognized even with a regular webcam. The main idea behind most works that employ this principle is to ask the user to match the motion of the desired target with the input device and compare the movement of the input device with the movement of the target using a given similarity measure. If the similarity between the input device and the target is sufficiently high, the target becomes selected. However, despite building upon the same principle, these works employ a wide variety of input devices, data processing pipelines, similarity measures, feedback mechanisms, and evaluation procedures, making it difficult to compare approaches and results to advance the state of the art. The challenge here is that the design space of motion correlation interfaces is enormous. Not only there are numerous parameters to be manipulated, these parameters are not necessarily independent, making it difficult to fully explore this design space. In this paper, we draw from probability and information theory to help us design better motion correlation techniques. We argued that a probabilistic interpretation offers a holistic approach for understanding motion correlation and a consistent language for framing future work and advancing progress on the topic. We begin by modeling the selection process as a Bayesian network, where the user behavior and the target motion are observed variables, and we want to infer the user's state, that is, which target they want to select, if any. This allows us to use Bayes' rule to formalize the principles behind this interaction, which you can check out in the paper. In a probabilistic approach, we turn the binary decision of whether to select a target into a more nuanced calculation of likelihoods, which is much more appropriate for this kind of continuous interaction. A key idea behind this approach is the modeling of the interaction process as transmission of information from the target to the user. We see the movement of the target as being our signal, which is going through a noisy channel and appearing as the user behavior on the other side. This way, if the user's state is that of wanting to select target A, it means that the user behavior we observe will be a distorted version of the target motion. We can then explicitly model the kinds of distortions that we went through in this noisy channel, such as the lag introduced by the sensor and by the user, and the spatial transformations due to calibration and differences in coordinate spaces, and the noise introduced by the sensor inaccuracies and poor user performance. Pulling these out highlights the assumptions that each similarity measure makes about the context of views. For example, certain measures assume an approximately similar scale in both motions, while others cannot tell apart targets that move in the same frequency. By looking at selection as transmission of information, we can reinterpret how previous works used similarity measures. Through this lens, we see the similarity as a way of estimating the mutual information between the motions of the user and the motions of the targets. That is, how much do we learn about what the user will do by knowing how the target is moving. In turn, this means that choosing a similarity measure depends on how well it estimates this mutual information in the context of use of the system. There are many lessons that can be learned by approaching motion correlation from a probabilistic perspective. In the paper, we demonstrate how previous works are still compatible with this, but can be enriched with a bit of probability and information theory. These theories help us understand how and why these techniques work, particularly when considering the selection process as transmission of information. It gives us a new lens to look at similarity measures by thinking of them as estimates of mutual information and bringing into the fore the assumptions they make about the context of use of the system. There is a lot more in the paper where we give you a step-by-step case study based on data from our previous work. We show how you can use empirical data not only to compute performance metrics, but for computing probability density functions. We also give you tools for evaluating your designs a priori, particularly for computing the entropy of the system to quantify the uncertainty of the inference, and computing the entropy of a given trajectory design to identify if there are points along that trajectory where the system is likely to find it difficult to tell motions apart. My name is Eduardo Velloso from the University of Melbourne, and this work was co-authored with Morimoto from the University of São Paulo. Thank you for watching.